Okay, so now let's look at the other topic here, fluid in motion. Okay, so far whatever we did had to do with what? Fluid in hydrostatic equilibrium, meaning the fluid was not moving, it was at rest, and it was not, so it was at hydrostatic equilibrium. Now the next part of this chapter is going to be about fluid in motion. So what happens when the object moves, how the physics changes once the object starts moving. Okay, so let's make some assumption here. So assuming fluid is ideal, so what kind of fluid is ideal? So ideal fluid has some of these characteristics. It has steady flow. There is something called laminar and streamline. We'll talk about that in a minute. It is steady flow. It is incompressible, so density does not change. Remember, then whatever these assumption will not be good for the gas, because in the gas, right, as we compress, first of all, gas is compressible and the density changes, right? So it is not good approximation for gas. For this ideal fluid, another characteristic is non-viscous, or it has no internal friction. Okay, so now let's talk about this little bit about the laminar flow here. Okay, so I have a picture here, another picture here for laminar and turbulent flow. So we have some fluid here. Some of the fluid are kind of going this way, kind of going counterclockwise, some are going clockwise, and then are in the different direction. When the fluid has all these different, it is flowing in all these weird different direction, that is referred to as a turbulent flow. But then if all the fluid here, they are moving in the same direction, and then all the particles are actually in the same direction, then that is called laminar flow. Okay, this is something like, probably if you have sat close to a river, you should have noticed that, or like rivulet, you see some water is kind of going like this, the other part of the water is kind of circulating on this side. That would be something like turbulent flow. For laminar flow, if you have a water flowing through pipe, and that would be mostly laminar flow. Now if you want to look at, like, in terms of here is this smoke here, so look at this part here. It's kind of, this part is kind of a little bit like this, so that part is referred as a turbulent flow. But then if you look at this down here, it's pretty smooth, and that part is a laminar flow. So when we say steady flow, it means the velocity of the particle of a fluid at every point, like here, here, or here, at every point is constant. Okay, so the velocity of the particle of a fluid at every point is constant, so the velocity is not changing. Okay, that kind of flow is called steady flow. Okay, incompressible, you guys already know, right? Okay. Oh, there is word streamline. You may say, what is this streamline? Okay, here is an example of streamlines. So we have a car here, and then you see this is really outside, like the air, right? Like the pathways for this gas, air, flowing air. So this line, this looks something like this. Kind of looks like this. They kind of goes like this, like this. These are the streamline. They never cross each other. Okay, so they are the distinct pathways for fluid to flow. Okay, so really streamline is like a trajectory. When you had a projectile, it would move in trajectory, right? The trajectory of the fluid is called streamline. Okay. So just a moment, guys. Oh, here is it. All right, so now let's look at the few things about this fluid in motion. So fluid in motion. Continuity equation. Okay? This is the one we are going to talk about. Let me look at my note here real quick. Okay, so let's consider a tube here which has a shape something like this, and then assume it has the shape changes afterwards, and then it has like that shape. Okay, this is too long. Okay, well, I think that's enough. Okay, so assume there is this cross-sectional area at this end is, let's call this as A1. Okay, and then assume this side, the cross-sectional area is smaller here, right? So let's call this as A2. Now the fluid is flowing here, so this is all fluid. I'm just making this here, fluid flowing through here. Okay, let's assume, so let's take this small, again I'm just drawing another cross-sectional area here. The reason is this, I want this part, so the distance between this, right, the whatever the fluid we have here, this fluid, this is going to, in some time, let's say sometime delta t, that's the duration of the time, it's going to move through a distance. Let's call this distance as delta x1. Okay, so the distance from here to here, the fluid, let's call this okay, so let's call volume, a small volume element delta v1. In time delta t, it is going to travel from here to this distance delta x. Okay, so here I'm going to make this. What does that mean? Something is here, this is like, this thing is traveling some distance like this, x, delta x, x1, okay, in some time delta t. Okay, that's what I'm saying. All right, now and then this has a cross-sectional area a1. Okay, that's what I'm just exaggerating here. Now if that's the case, can we write this volume of the volume element that travel in this delta time as volume delta v1 equal to what? Can we write it? This is a cross-sectional area, right? So this is, I'm going to make another diagram here. So it's like this. If you make that cylinder upward like this, I think it would be easy for you. So this is like cross-sectional area of the cylinder, and then it is traveling some delta distance delta x. Okay, so if it is like h, and this is like area a, and then how do we find volume? Volume equal to area times the height, right? Same concept here. So that change in the volume, or that volume element equal to, we can say area 1, cross-sectional area a1 times delta x1. Okay, so this delta b1 can be written as a1 delta x1 here. Now this is an ideal flow. Okay, here we are considering this fluid is flowing under the ideal condition, or this is an ideal fluid, right? So now in that same duration, okay, so whenever, starting from this time all the way to the time it took this volume element to reach here, the same amount of the fluid must be flowing through this part also here. Okay, so this is the cross-sectional area A2. In some time delta t again, the amount of the fluid that's flowing there must be so this is another cross-sectional length, so it must travel the distance delta x2, and then the volume must be the same, which means delta v2 must be equal to a2 delta x2 here. Okay, so this volume element must be equal to this amount of the volume, or don't look at the equation, imagine this amount of the water that was flowing from here to here in this same time, let's say 5 seconds, must be equal to the amount of the water that will flow in 5 seconds from this from this distance. That's what it means. So let's say 1 liter of water was flowing here, 1 liter of water must flow here in 1 second. Let's say both of them were flowing in 1 second, that same time duration. Okay, so that is the important thing. Now since fluid is incompressible, we can write, since fluid is incompressible, we can write delta B1 must be equal to delta B2. Okay, so when we do that, then we will just substitute this A1 delta X1 must be equal to A2 delta X2. Okay, now let's divide this equation here, this equation, by time interval delta t. We can do, right, on the both side. It's just, we are just doing this, and I'm gonna write this down up here. Okay, so I'm just gonna erase this here and then erase this part as well. Oh, maybe I'll just write this down actually from here. Guys, go to this way. So can you see this quantity here, delta x2 by delta t, or delta x1 by delta t, has to do with what? X by t is what? This is equal to the velocity, right? Or speed of object there, right? Or in this case, fluid. So A1, V1, let us call this B1. This is separate B than this one, okay? It's lowercase b, B1. Speed of the fluid here, B1, at from, during this interval here must be equal to A2. This delta x2 by delta t can be written as v2. Okay, so this is called the equation of continuity. What does this say? If the same volume, if this, the volume is constant, if the same volume of the water or a fluid is, passing through cross-sectional area A1, and then if it is the bigger one and it is passing with some speed V1, then when it reaches to the smaller cross-sectional area, it must pass with the higher speed. Okay, because this A1 B1 equal to A2 B2, this is constant. Okay, so that's why you would see that when you have a water and a hose, actually if it is at first, and the tube, if the tube is the bigger, and then it is moving with the smaller speed, but then by the time you make it a really small tube on the the hose, the tube, then it is gonna start really going fast. Okay, so that is the equation of continuity. From equation of continuity we can derive another quantity called volume flow rate, represented by Q, and then this volume flow rate is really the volume of the fluid, volume of the fluid flowing per second, Q, and this is given as Q equal to delta V by delta T. Okay, delta T, but you guys remember delta V by delta T. Okay, what can we write here? Delta V is what? Can we write delta V as area times delta X, right? And then delta T. So this quantity, you can write it as B, right? Lowercase b, speed. So Q is A times B. Okay, so volume flow rate is constant. This quantity is constant. Unit of this quantity is what? Area is measured in meter cube, meter. Volume is, sorry, speed is measured in meter per second. So meter is squared, area is measured in meter is square, right? Meter is square times meter would be meter cube and per second. Okay, so that's the unit. All right, so that is about it for this lecture. Oh, let me give you this guy. So maybe this is something I think would be okay. So guys, again, go through this derivation. Please try to do it on your own after watching the video and see if you can get to this equation here and then this equation here. And then if you have any question, please do post it in the course discussion section. Okay, so this is something for you to try at home. Observe the flow of a water from this faucet, and then how does this diameter of the stream water changes as the water exits from, you know, this point all the way to here. See the diameter, how does it changes? Can you describe what you see? Can you describe what you see from the continuity equation? Okay, so this is for you to try at home and come up with the answer. Alright guys, so that's about it for this lecture. I'm gonna leave you guys here today. Take some time, review the lecture, read through textbook, and then we'll start with Bernoulli's equation in the next class. Okay, bye bye.